So good morning, everyone. Welcome back. I'm stoked to see all of you. Our divergent paths have converged to the source of our calculus community. So I look forward to spending this day and one more day, class day tomorrow, with all of you, kind of as a group. So it's such a blessing. All right. This is it. This is the last section of calculus. For many of you, this might be the last bit of math that you may ever take, which is kind of tragic. For others of you, will have the joy of taking more math in your program, so you're lucky in that. But for some of you, this could be the end, and it's kind of both a bittersweet moment, I think. And certainly in calculus, this will probably be the last calculus class that many of you will take, last topic. And after that, all of our paths will diverge. And so it'll be kind of a sad moment. But we get to enjoy it while we're here. And so before we dive into the divergence theorem, I wanted to spend a few more minutes talking about curl. There was one more illustration / example in the Stokes theorem section, and I think it's important simply because it helps to reinforce the visual element of curl. And I think that the more you have an intuition about what's going on, the more these topics are likely to stick with you beyond this class. So let's continue where we left off yesterday with one more mini example. All right, so again, this is the very end of section 17.7 on Stokes theorem. And the important part here is the intuition. So consider the velocity field v equals 1 minus x squared, 0 comma 1 minus x squared comma 0 for -1 less than or equal to x less than or equal to 1, and -1 less than or equal to z less than or equal to 1, which represents a horizontal flow in the y direction. So in A, suppose you place a paddle wheel at the point 1/2, 0, 0, using physical arguments. In which of the coordinate directions should the axis of the wheel point in order for the wheel to spin? In which direction does it spin? And then what happens if you place it at another point? And so let's look at the manipulate. All right, so imagine that this is this is the flow in some sort of a river. And so I sort of think about it like there's the banks of the river here, something like that, and then we put our paddle wheel in, and this way we put the paddle wheel in kind of going with the current, and notice that it's not going to spin at all. If we put it in this way, again, there's a lot of pressure on the paddle wheel. It could break, but it's not going to spin because everything is just sort of hitting it directly. But if we put the paddle wheel in like facing up, then notice that the paddle wheel is indeed spinning. Why is it spinning clockwise?
There's more net on the right.
Yeah, exactly. So there's kind of long vectors on the right, short vectors on the left. So there's kind of more force hitting the wheel on the right side, causing it to spin around this direction. What would happen if we moved our paddle wheel over to here on to the other point?
Spin the other direction.
It'll spin the other direction. Wow. So if we go over to here, it's now going to spin the other direction because there's more velocity on the left. So where won't it spin at all?
Where both sides balance.
Yeah.
Equal forces.
Yeah.
Directly.
Right. So right in the middle, there might be a lot of force on the wheel, but it's not going to spin. It's kind of interesting. I don't have a lot of experience with rafting or anything, but this was kind of interesting because I was thinking about how when you're on the edge, when you're in the center of the river, even though the current is the strongest, you don't really rotate that much. But it's when you're on the edge that you start to rotate for this very reason. There's all that, I don't know what you call it, friction. I don't know what you call water friction on the edge of the river and the current. And then things are going faster in the middle, and that's going to create this tendency to rotate. I was like, oh my gosh, I now understand better understand my whitewater rafting experience, which is kind of cool.
So like if you were at the edge, but your nose then points towards the middle, and then it'll like throw you back the other way.
So let's see if we could figure it out. So if we stuck our raft here, right, it's gonna have a tendency to drive the raft. The current is gonna have a tendency to drive the raft toward the shore.
Yeah.
I mean, obviously, this is assuming there's no rocks or anything like that. But that was kind of cool. Does this make sense in terms of the kind of how you could see the direction of the curl based on the length of those vectors? Any questions about that? And again, the other thing to note is that notice that it's spinning here where notice that the axis is pointing up. So the axis is perpendicular to these guys right here, right? And versus if we rotate our wheel, we're not going to have any spinning because we're not going with the curl. Let's do it mathematically. I think that'll help. I mean, I guess that was mathematically, but let's do it in symbolically. That's probably a better term. Okay. So we talked about this stuff. So if we compute and graph the curl, so when we go through our curl calculation, we end up with that the curl is just going to be this negative 2x in the z direction. And so you can see that right there where it goes to the origin, you'll have 0 curl. That means there's no rotation. We saw that in the picture earlier. When we had x's that were positive, in this case that would be on the left, then we had a negative curl, and that negative curl is corresponding to the clockwise rotation. Versus on the other, when x was negative, so this is the second point, we had positive curl and clockwise rotation. So the curl points in the z direction, which is the direction of the paddle wheel axis that gives the maximum angular speed. Pulling all this stuff together, so if we interpret it as the previous example shows, the direction of curl F, or del cross F at P, is the direction in which you should orient the axis of a paddle wheel to obtain the maximum angular speed. I'm not asking if curl is your best friend in the world, but given that many of you had never done anything with curl just a couple of weeks ago, do you feel that you have some sense of intuition about what curl is and how to visualize it? I've got one thumbs up, a couple thumbs up.
Yeah, this makes a lot more sense than the kind of abstract stuff we were talking about earlier.
Yeah, that's cool. Yeah. For those of you that are doing physics, well, I think specifically stuff with electricity and magnetism, I hope that this is helpful and also corresponds with what you're learning elsewhere. All right. So let's begin section 17.8. This is the last section in the text, last section in our course, and it's on the divergence theorem, which is also called Gauss's theorem. So vector fields, which we've been studying, can represent electric or magnetic fields, air velocities, and hurricanes. We just saw a video. What was it? It was like one of those. What do you call those videos where they talk about movies? I don't remember. It's not a review or a trailer, but it was talking about the film Twister from back in the 90s. So. And the whole point, for those of you that have seen it, and the whole point of the film Twister is to try to take probes and send them up into a tornado, and in sending them up into a tornado, we'll be able to find the air velocities inside the tornado. Like, it's literally to figure out what those vector fields are, which is pretty cool. So anyway, sort of the blood flow in an artery. These and other vector phenomena suggest movement of a substance. So a frequent question concerns the amount of the substance that flows across a surface. For example, the amount of water that passes across the membrane of a cell per unit time. Such flux calculations, remember flux is the amount of stuff going across a surface, may be done using flux integrals, as done previously, or these could be surface integrals. Like surface integrals. So surface integrals, as we did previously, but the divergence theorem offers an alternative method. In effect, it says that instead of integrating the flow in and out of a region across its boundary, you may also add up all the sources or sinks of the flow across the region. It's kind of our background. Like we did in the last section, I'd like to spend a little bit of time looking at the parallels between theorems. So throughout this section, we've been drawing parallels between theorems, and the divergence theorem is no different. So there's two bits. This first part is talking about Green's theorem, and this would be connecting to Stokes' theorem. And here we're looking at the circulation form. So remember that there's two forms of Green's theorem. There's the circulation form of Green's theorem, and there's the flux form of Green's theorem. Do you remember how to tell the difference between them just from the formulas? Circulation focuses on what? Flux focuses on what?
Dot and cross?
Yes, dot and cross, but I'm looking for something else.
The plus and minus.
The plus and minus, yep, that's true as well, but I'm looking for something else.
Curl and divergence.
Curl and also true, but I'm looking for something else.
The normal component and
Tangential component.
tangential component.
Yes, Robert and Melissa. So here in the circulation form, we're looking at the tangential component. So this is the tangential part of the field, and you can see it showing up here in that T. And in the flux form, you're looking at the normal component of the field. And you see it showing up in this N right here. Okay. How else could you write the line integral of f dot t ds? I was trying not to clutter it with too many versions, but you could also write this as the line integral across C of f dot what?
dr.
dr, exactly. This version over here on the right, this is the one that we've used the most, but I chose to write it with the tangent, with the t ds here on the left, because I wanted to make a clear parallel between the circulation and the flux forms. So in 2D, we have the circulation form of Green's theorem, which says that the line integral is equal to the double integral, and that's Green's theorem. And in flux, you have the line integral of f dot n is equal to the double integral, the divergence, and again, this is Green's theorem. So then what we did in the previous section in 17.7 is we talked about Stokes' theorem. And in Stokes' theorem, we had the same bit here. Like these two things these are the same. But now we're in 3 dimensions. And instead of having the 2D curl, now we have the 3D curl. And then for the divergence theorem, we're basically doing the same thing. The 2D version was f dot n, and we ended up using the 2D divergence. Here we'll have a surface integral. So notice this is a double integral / surface integral here. And so it's the surface integral, and it'll be equal to the triple integral of the 3D divergence with respect to dv. Are the parallels between the theorems clear, at least in terms of the formulas? Okay, I'm getting some thumbs up. Let me just point to one thing. When we're talking about flux. So when we're in the 2D version, we have some curve C, and then we might have some surface here. And when we're looking at the flux, what we're looking at is the normal component that's going outward across the boundary. Oops, not that one. It's got to be perpendicular, right? But when we're looking at the 3D version, now suddenly there's going to be a surface. So this is our S. And when we're looking at the flux, what we're looking at is the perpendicular components across the kind of the outward part across a surface. And so it's almost like the units are different. That in the 2D version up here, you're looking at the outward motion, but it's linear, it's across a line, whereas here we're going to be looking at the outward motion, but it's going to be across a surface. So it's in terms of area. All right. And also note that in order for the divergence theorem to hold, we're going to need this thing to be a solid. And so there'll have to be actually be a bottom. So this is going to require a closed solid or a closed surface. Questions? Cool. Very good. All right. So let's look a little bit at the interpretation here. So here, there's like a whole bunch of stuff going on in this paragraph. So this paragraph here is a reference to the 2D statement up above. So the line integral on the left, this yellow thing, gives the flux across the boundary of R, just like we were talking. The double integral on the right, this pink thing, measures the net expansion or contraction of the vector field within R. So if F represents a fluid flow or the transport of a material, the theorem says that the cumulative effect of the sources or sinks of the flow with R equals the net flow across its boundary. I think we talked a little bit about them. Do you understand this idea of a source or a sink?
That's just relative to the direction.
Like, is stuff being materialized from the spot, or is it all being sucked into the spot? So probably the most famous example of a sink would be like a black hole, right? Everything is being sunk, drawn into that spot. The most famous example of a source would be like a spring of water, right? There's like this hole in the ground and stuff keeps coming out of it. It's like the source of something. So the divergence theorem is a direct extension of Green's theorem. The plane region in Green's theorem becomes a solid region, and the closed curve in Green's theorem becomes the oriented surface S that encloses D. The flux integral in Green's theorem becomes a surface integral. The double integral in Green's theorem becomes a triple integral over the three-dimensional divergence. So basically just saying we've gone up a dimension. Plus one dimension. Here it's 2. Here it's 3. And same over here. Here it's 1. Here it's 2. Questions? Very good. All right, let's look at this manipulate and see if we can understand what's going on. All right, so first of all, remember that the divergence theorem has a surface integral on the left and a triple integral on the right. And so here we're focusing in on the surface integral on the left. And notice we are interested in which component of the field.
Normal.
Yeah, so we're interested in that normal component of the field. Good. So notice if at this point that's given, notice that the field is pointing kind of towards us. The normal component is perpendicular. How much of this is going to, how much of F is going to count toward the towards the surface integral?
Well, looking at the manipulate, F looks like it's tangential, so is none of it.
So none of it, exactly. So it looks like F dot N, it looks like it's around 0, so it's not going to count anything toward the surface integral. So we could move stuff around and see if we could find another, let's see if we can find a spot that's a little bit more interesting. There's lots of zeros. I'm trying to find something that doesn't look like it's 0. Yeah, there's one that's a little bit bigger. All right. So here, field is pointing this direction, the normal component's pointing that direction, and so we're going to get a little bit of F dot N that's counting towards the surface integral. So we're going to get a little bit more there. If we, here they're closer to perpendicular, so less is going to count. And so we're just kind of going across the entire surface, and at every point on that surface, you could sort of imagine taking that surface and splitting it up into all those little patches, and each one of these patches we could ask ourselves, well, how much is this going to count towards the surface integral? Well, we're going to ask ourselves how much of the field is normal to the patch, basically, and we'll weight it by the size of the patch. So that's what's going on the surface integral side. Ready for the divergence theorem side? Very good. All right, so let's look at the divergence theorem version. Okay, so let's see what's going on here. So notice at this point here, the divergence is positive. And so see the little sphere, how the sphere is getting bigger? That sphere getting bigger is representative of this idea that there is no divergence. So then somewhere in here, it looked like it was bigger. So see how it's expanding faster there? Faster and faster. Whereas here it's growing much more slowly. So the speed at which that sphere is growing, right here. Let's see if I can. The speed at which the sphere is growing is telling us something about the divergence. So here it's growing pretty fast. Okay. Now here, what's interesting about the sphere is now the sphere is shrinking. Notice it's negative up above, a little hard to see, but so the spheres are getting smaller, and that's reflective of the fact that you have negative divergence. Kind of like faster negative divergence. And so would this point P that we're looking at, would this be a source or a sink?
Sink.
So this point would be a sink. In the divergence, let's see if we can put the field on. Let's see what it does. Let's see if that helps. Hard to tell whether that's, hard to tell what's going on there. So this is just looking across the surface of the sphere, but when we're dealing with the divergence theorem, it's important to note that we're actually going to also look at the interior of the sphere and ask what would happen if we stuck all those little balls and asked, do we have sources or do we have sinks inside the sphere as well? So looking back up here at the top, we're looking at the triple integral of the divergence. And so we're going to go across the entire sphere and look at all these little chunks of the sphere, like solid, all the way to the center of the Earth, if you will. And at each point, ask ourselves, is it a source or is it a sink, and how much so? And we could add all of them up. And the cool part is if we add up all the stuff that's going on the inside, it would be equal to figuring out what's up with that surface integral on the outside. Questions about how to visualize the divergence theorem? Oh, let's see if this will do it. Oh yeah, let's see if that did it. No, it's hard to, am I now inside the ball? I can't tell. Oh yeah, there it is. Yeah, so there we can go all the way around everywhere and figure out, is it a source or a sink, and we're inside the ball, and then we come a little bit closer to the surface. Is it a source or a sink? Is it a source or a sink? And if the triple integral hits all of the points on the whole sphere at every possible radius from the center of the sphere out. Ready to do it and actually run through the calculations? Very good. All right, so here's the theorem and our first example. So the divergence theorem. Let F be a vector field whose components have continuous first partial derivatives in a connected and simply connected region D enclosed by a smooth oriented surface S. Then the flux, which is the normal component of the field across the surface, is equal to the triple integral of the divergence across the volume. All right, so let's do it. And let me switch over to the doc cam for this. All right, so I abbreviated the wording here, but the question is that says, suppose you have a sphere S right here that's oriented outward, and we want to use the divergence theorem to find the flux through this field across the surface. And so you have a ball, and we're asking how much stuff is going out of the ball. And so if we were to do this directly, we could parameterize the sphere with two r of uv and evaluate some sort of surface integral. But instead of doing it directly, we're going to do it indirectly using the divergence theorem. So the flux, the formula for flux is the surface integral of f dot n ds. And this is again the big S. And we just learned our divergence theorem. And just to make it clear, the S here would be the surface of the sphere. And so this would be equal to the triple integral of the divergence of F dV across the interior of the sphere. So before worrying about limits of integration on this triple integral, let's start by figuring out what the divergence of F is. So this will be triple integral across our region of the divergence of F. So that would be partial with respect to x of 0, which is 0, plus partial of 0 with respect to y, which is 0, plus partial with respect to z of z, which is 1, dv. So 0 plus 1 is pretty close to 1. And so the question is asking us to evaluate a triple integral across d of 1 dv. As soon as you put a 1 in for your integrand, what does that make this triple integral represent? It'll be equal to what?
Volume.
Yeah, so this thing, you can think about this as the volume of the sphere. Now, it's kind of interesting because flux is not the same thing as volume, but from a mathematical standpoint, the magnitude, the number that's coming out is going to be the same. And so in this particular case, we have a sphere, radius A. And so what's going to be the volume of that sphere? You guys remember that formula for the volume of the sphere?
4/3 pi a cubed.
4/3 pi a cubed. Very good. Wow, we just evaluated a surface integral using a triple integral in 1, 2, 3, 4 lines. That's pretty good. Now, granted, it was a little simple, but that was pretty nice. Questions about this example? Okay, so again, what does this 4/3 pi a cubed represent in this case? Yeah, this is the hard part. So this represents the
magnitude of the net flux.
Yes, it's the flux, and I think it's more than magnitude. I think it's just straight up the flux, the net flux, because magnitude would imply no sign. And then what is flux? We were talking about curl. So how do we understand flux again? So given the silence, let's look ahead in our notes at the next section that's called Interpreting the Divergence Theorem. We're talking about flux. So interpreting the divergence theorem, understanding flux. So suppose that V is the velocity field of a material. Suppose that's what we're talking about, such as water or molasses. I don't know why we choose molasses. Have you guys even eaten molasses? Like, what a strange thing to choose. But anyway, I like the molasses cookies. They kind of have a fun bite to them. So such as water or molasses, and rho is a constant, is its density. So the vector field that's made by taking the density times the velocity would describe the mass transport, like how much mass is being transported or moved of the material. So that means F gives the mass of material flowing past a point in each of the 3 coordinate directions per unit of surface area per unit of time. So like, it's like imagine that you're in a river and you're sitting on a rock. I wonder if we could draw it. So there's some sort of a river here. Ooh, we need a blue river. There's some sort of a river here. And maybe there's a rock that's sitting out here. And here's Dusty with his fur hat. And I'm looking for the divergence, and so I'm asking how much water is going in each direction. So I'm asking myself, how much is going in the Y direction? How much is going in the X direction? How much is going in the Z direction? So the vector field describes the mass transport of the material. This means F gives the mass of material flowing past a point per unit. So if you think about it, it's saying, are we looking at a single point? Am I looking at something the size of my fist? Am I looking at something the size of the boulder? And so you can imagine that the mass is going to depend upon the surface area kind of that we're considering. And it's also going to depend upon the unit of time. Are we asking how much water has flowed by in a second, in an hour, right? It's going to those are going to very much impact the outputs. So when F is multiplied by an area, the result is flux. So F somehow times area. This is a little bit bad math because of the fact that you have, this is a vector field and this is a scalar quantity. That's why we end up with the dot n here. Will give us the flux, at least in that direction. So the divergence theorem shows that the net flux, or mass being transported across the boundary, is equal to the net divergence across the region inside the surface. More succinctly, the flux of a material across the boundary is the cumulative effect of all the sources or sinks within the region. So going back to the question, how do we visualize flux? Think about it. I think you could visualize it as it's the stuff flowing across a surface. Okay. There's a lot of motion that's happening in these concepts, and so it's challenging to draw a static picture. But it's the stuff flowing through a surface. All right. I think we have enough time to do one more brief example. So in example 2, we are going to let S be a cube oriented outward. It's in the first octant, and each of those side lengths is 1. And so let me just draw the picture. Each of these lengths is 1. Okay, and we're trying to find the flux. So that if you want to calculate the flux directly, you're going to have to use a surface integral. And if you want to use a surface integral, what's going to be the very first step?
Parametrize?
So to use a surface integral, you're going to have to parametrize. And how many things are you going to have to parametrize?
6 things.
6 things, which is a good reason to look for another method. So we have that flux is equal to the surface integral across the outside of the box. And we'd really prefer not to deal with this. So this would be f dot n ds. But good news, this is a closed surface. We can use the divergence theorem. This will be the triple integral across the inside of the box, or the volume of the box, of the divergence of this thing. So that would be the partial with respect to x of 2x, 2, partial with respect to y of 3y, partial with respect to z of z squared, 2z, and this will be dv. Questions so far? Very good. All right, so crunching through this triple integral is not too bad. So we're going to get the triple integral from 0 to 1, 0 to 1, 0 to 1 of 5 plus 2z d, maybe we'll go dz dx dy. So this will be 5z plus z squared from 0 to 1, which is a funny way of writing 6. Which altogether will give us just 6. So what does this 6 represent?
What?
Represents the flux, or in other words, it's the amount of stuff that's going out of the box. Is the box itself a sink or a source?
A source.
A source. You have positive flux. There's stuff leaving, more stuff is leaving the box than coming into the box. So we have a source, which is pretty cool. And by using the divergence theorem, we calculated 1 triple integral instead of having to break this surface integral up into 6 different mini surface integrals because of the different parts of the surface. So these are these first two examples have been pretty straightforward, but I think they've showed you the power of using the divergence theorem right here at the get-go. Any last questions? Very good. Well, thanks everyone for being here today. I look forward to talking to you all one last time tomorrow in class as we wrap up our divergence theorem and also kind of look very briefly at some of the connections that this has to physics and to Maxwell's laws from electricity and magnetism. So have a wonderful day, everyone. As our paths diverge, I hope you two are stoked about the idea that they get to reconverge one last time tomorrow. Take care, everyone. If you have questions, feel free to hang on the line. See you tomorrow.
Hey, Dusty.
Take
Bye,
care.
Dusty.
Thanks for the lecture, Dusty.
Oh, thank you, Enrique. I'll see you tomorrow.
Cheers.
Cheers.
I have a question about the homework.
Go for it.
Uh,
Do you want to share your screen, Vu?